So maybe I think historically I usually say a few words. So hey guys. So I'll just say that Vishakha, I just did some calculations, is my 25th student. That includes counting every student I supervised either with Ray or with Narayan as mine, right? Of course, they can count those students also. And I think barring unforeseen circumstances, Vishakha is my final student. So 25 seems like a nice number. And I'll just say that we started working together in the summer of 2020, in the pandemic. And she is my first and only student who I've met almost exclusively on Zoom. But I don't think it's really, I don't think it's hurt our relationship. I think it's been surprisingly effective and agreeable. And I'll say one more thing, which is I've now been working on Age of Information stuff almost 15 years, since maybe 2010. And you know, sometimes you think, well, has it run its course or not? But in fact, working on this thesis, the thesis, her thesis, really shows that there are lots of interesting and important problems still to work on. So in fact, I think the area has still a long way to go. So it's really a pleasure seeing this defense, and I'm quite pleased myself with how the thesis has turned out. Thank you.
Thank you, Professor, for that written speech. So I'll just now kind of start with the talk. First of all, thank you everyone for being here in person and those who are online. I'm going to talk about our work that is titled Storing, Retrieving, and Processing Updates, Timeliness Perspective. So
did something happen? Because now there's just a box that says common.
I don't know, this is...
You have to click on the presentation.
Yeah, but focus back on the slides. Yeah.
Oh, thank you. Yeah. So a lot of things can go wrong at the city's intersection. There could be a reprobate drunk driver, people violating all sorts of traffic rules, pedestrians jaywalking while looking down at their phones, people jumping red lights, and sometimes, unfortunately, even an open manhole. Thankfully, technology can help solve most of these problems. So, for example, there could be a smart city intersection where the camera mounted at the intersection captures the live traffic conditions, sends these frames to some nearby edge server that maintains some database, and these frames are recorded in the database. And then this edge server can have many services running, for example, traffic signal management, smart parking, and even collision detection system. And so one of the services, say, for example, collision detection system can use these frames that are recorded to do some advanced collision detection thing, and then send the update back to the green car, in this case, that, oh, there is a pedestrian in front of you, so just brake. Alternatively, if you consider a much more non-real-time application, for example, MapReduce, where the way this works is that input files are processed in parallel by some mappers that can be running on different machines. These mappers generate intermediate data that is subsequently stored on local disk. And then the reducers retrieve this data to work on them more and process them asynchronously. Again, each instance of the reducer could be working on a different node. So what we see is that whether be it an application that is real-time or non-real-time, at the heart of these applications lies a producer-consumer paradigm, where producers are some software components that generate data or updates which are subsequently stored in a shared space. And the consumers, on the other hand, retrieve this data to process upon them asynchronously. The good thing about this paradigm and why it's prevalent in modern applications is that it fosters loose coupling between the components. So this means that you can have multiple producers running in parallel or multiple consumers running in parallel. And not only that, it promotes heterogeneity, meaning you can have many consumers working on different timescales. So smart parking perhaps is not like much real-time service, but collision detection is. So both of them can work as a different consumer service. Okay, so in this thesis, our objective is to investigate timeliness in storing, retrieving, and processing of updates, particularly in producer-consumer systems when memory is used as an information dissemination. And for that, we focus on a class of systems where there is a source that generates source updates. These updates are recorded by a writer in the memory, and this generates an age process, which we refer to by X of t. Then there is a client that is interested in these source updates. So the reader on behalf of the client reads the memory, hands over the updates to the client. This generates another age process at the client input. And then the client uses these updates to perform some sort of processing or computation, and then delivers the processed update to the monitor. When it does that, this results in another age process at the client output, which we represent by Z of t. So just to put things into context, the application that I just described before, here the camera would act like as a source. The reader-client pair could be assumed to be the collision detection service that is running, and the user, the green car and the pedestrian could be thought of as the monitors. Okay. So this is just trying to give you an overview of how the age evolves in the memory. So the upright triangle instance corresponds to when the source update arrives at the writer. So in this case, source update arrives fresh, meaning with age 0. The writer takes some time to write to the memory. So when it writes, the age is reset to the age of object, which in this case would be just the time elapsed for the writer it took to write to the memory. Similarly, in the green sawtooth waveform corresponds to the age evolution at the client input. So when the reader reads, it gets an object of from the memory of age X of t. So Y of t is reset to X of t. And in the absence of any read, the age continues to grow at unit rate. Okay. So, but when you use memory as a means of information dissemination, there are a couple of challenges associated with it. So for example, consider this scenario where the mobile is, sending some updates. And in this case, it's sending location updates. So this update arrives with timestamp T1. The writer records this update into the memory. And now the client wants to kind of work on this. It starts working on it. But after some time, the user moves. It generates a new update with timestamp T2. The memory is updated. So we see that the age of the object is reset because a fresh update was written. But the client is still working on the green update and the older update. And what is happening is client is only getting the samples of updates published in the memory. It's not getting all the updates. What we want for the client is to work on the updates that offer timely representation of the real world. Well, then you say that, well, okay, the reader should just read often and often. But the problem is that the memory access is usually regulated by synchronization primitives to prevent data inconsistencies. And in the literature, there are two broad classes of primitives, log-based and logless. We use readers write a log as a candidate to study the log-based primitives, and it works as follows. So you have a reader that is reading a data item from the memory. It has to put a read log. And if the writer wants to update that data item simultaneously, its request will be denied. On the other hand, if the writer is writing to the memory, it's updating the data item, it has to put a write log. And if the reader wants to read this item, its request will be denied. A lockless construct, which allows concurrent forward progress of both readers and writer, is called as read copy update. And it works as follows. So suppose this reader is reading a data item and the writer wants to update this data item. So it will just create a copy and modify the copy. Now, when the new read request arrives, it will always read the latest copy while the old reader would continue accessing the same copy. Okay. So remember, our goal is to have updates in the memory with the client and ultimately with the monitor that should offer timely representation of the real world. Well, we can minimize x of t by writing frequently, but if you were using a log-based primitive to protect the memory access, that would block out the reader and thereby increasing the age at the client input. Alternatively, if you were using a lockless primitive, then the way you'll write frequently using lockless primitive would be you have to create many copies, and this will increase memory usage. You can minimize y of t by reading frequently, but again, with log-based primitive, this will block out the writer. And with lockless primitive, we just saw that it's still not guaranteed that the reader will always read the freshest update. Okay, so it looks like there is no straightforward way to kind of optimize these age processes. And in this thesis, we try to tackle this question of, well, how can we minimize x of t, y of t, and z of t as age processes? And as such, the work under this thesis can be divided into three broad themes. In the first part, I'll focus on kind of talking about policies to help readers minimize the age at the client input. In the second part, we'll focus on understanding the impact of synchronization primitives on the age of update in the memory and age of update with the client. And finally, we'll talk about how the client can optimize its computational resources to timely process the update such that this age at the monitor Z of t is minimized. So for the first part, we'll just assume that readers have unrestricted access to the memory, and our focus here will be to kind of hopefully find optimal policies for the reader under broad class of systems that we have studied. So in this work, for this part, we'll focus on a model where there is a charge associated with sampling the memory. Now, this cost structure usually varies between systems. So for example, in systems where the object size is large, then retrieving the object takes longer time, so it's much more expensive. On the other hand, timestamp retrievals are relatively cheap. There are scenarios where the object sizes are small, so retrieving the data item and the timestamp have kind of comparative latencies, and this is usually observed in scenarios where queries are sent to a distant database. And in this work, we focus on the former class of systems where we assume that the readers, by virtue of inexpensive timestamp retrievals, know the state of the memory. So they kind of know the source update age in the memory. And to study this system, we consider a discrete time slotted system where an update is published in a slot with probability P. The reader decides to read in each slot, whether it should read or not. Note that this model is consistent with RCU. So this means it's a kind of a lockless construct where the writer can write in a time slot T while the reader reads the current update. And our goal here is to find an optimal policy for the reader that minimizes the average cost that comprises of age of update with the client plus the cost incurred due to sampling. So if the reader samples, it will incur a cost of y plus c at time slot t. If it doesn't, then the cost is just y. Before kind of diving deep into understanding the system, I just want to point out some of the technical challenges associated with the problem. So to study the optimal policy, we had to formulate this problem as a Markov decision process, where the state is a tuple. Of course, you have to keep track of ages of update in the memory as well as with the client. And our objective is to find the policy that minimizes the expected average cost. The issue with this MDP is that it involves an average cost optimization over an infinite horizon, and the state space is countably infinite, meaning because the age can grow unbounded. The issue is that for such MDPs, optimal policy, whether stationary or stationary, might not exist. And thankfully, in 1989, Lynn Sinnott provided sufficient conditions for a Markov decision process to have optimal policies. And in our thesis, we do verify that those conditions are satisfied by our problem, and hence a stationary optimal policy does exist for this problem. Okay, so now that we know that an optimal policy does exist, we can kind of expend our efforts into finding one. For that, let's understand the system better. So suppose at time slot t, the state of the system is as follows. The age of object in the memory is x. The age of object with the client is y. And the reader decides to read, so it pays a sampling cost c. It takes one time slot to read. So when it reads, y is reset to x plus 1. Why? Because it took one time slot to read. And in the memory, in that particular slot, the memory could have been updated. So x could be 0, or if it weren't, so x goes to x plus 1. We see that when it read, it obtained an age reduction of y minus x plus 1. What we want for this system so that we are able to minimize the average cost is to have a larger age reduction such that it is worth the sampling cost and it justifies the cost of sampling. Okay, so now that we know what we want, we can kind of talk about what the reader should and shouldn't do and develop some intuition. So suppose the state of the system is as follows. There is a new update in the memory. The reader gets to know there is a new update. And the reader says, well, if I read, my age reduction would be y minus 1. And says, well, this is not good enough for me. It's not worth the cost I'll pay for sampling, so I'll not read. So it skips reading. In the next slot, the memory was not updated. So x goes to, from 0, it goes to 1. And since the reader didn't read, y is now y plus 1. And the reader now has to again decide whether it should read or not. Well, I think the reader should not read. Why? Because the age reduction remains same. It's still small as it was before. And so the optimal thing intuitively for the reader that it should not read. On the other hand, if the state were, suppose there was some other y, where the reader decided that this age reduction is large enough for me, so I should go and read. Then the question is, well, if the state were 0, y plus 1, what should the reader do? Well, we see that the age reduction is much larger than before. And so this is kind of an optimal thing for the reader to do would be to read and pay the cost of sampling because it justifies its reading. So we see that this optimal policy is kind of a threshold-based structure. And not only that, remember our state space was countably infinite. But because of this special state 0, y, our decision to sample or not sample has only reduced to considering only this subset of states. And in the thesis, we do show that our intuition holds. So if the reader didn't sample in 0, y, it shouldn't sample in the subsequent states as well until the memory is updated again. On the other hand, we show that there exists an optimal threshold such that if the age at the client input is some greater than optimal or is greater than some optimal threshold, then it should read and idle otherwise. We do provide an analytical expression for this optimal threshold in terms of the cost paid due to sampling and the probability that the memory is updated in the slot. And here I'm plotting optimal threshold as a function of P. There are two observations. First, we see that the threshold goes up with sampling cost. And in fact, this goes up with square root of 2c. And this is evident from the plot as well as from the analytical expression as well. The other thing is, as P is small, Y0 star approaches 1. So when P is small, this means that the memory is updated infrequently. Intuition suggests that this threshold should be very large because it could be that when the reader reads, the memory was not updated and it got the same value. So at first, this result might seem counterintuitive. But the reasoning is as follows. Recall that the sampling, if it happens, only happens in that state 0, y. Right? So when P is small, the age at the client is so large that it somehow behooves the reader to just go and read whenever the memory is updated. Okay, and this Y0 star equals to 1 is just acting as a proxy. Okay, I mean, if you don't read now, you're gonna pay a lot in terms of age. On the other hand, when P is approaching 1, this means that the memory is almost always updated. So, so the reader should be very stingy, and in some cases, it should be parsimonious in reading because the age reduction that it will get will not be significant enough compared to the cost it would pay for sampling. So this was like a counterintuitive thing that I wanted to discuss. And in the next part, we'll talk about system models under this broad umbrella theme of optimizing memory access, where I'll assume that the readers now, instead of having like a deterministic read time, have random times to sample. And we'll see how optimizing the age at the client input also optimizes the age at the client output. And for that, we'll focus on a class of systems where, in this case, reader is not aware of how the updates are recorded in the memory, and so it doesn't know the source update age. Okay, and we'll assume that the client takes some computation time to process the updates. And so this we consider continuous time system where the reader only reads after the client finishes processing. And so as before, the age at the client input will be reset to the age of object of the memory when the reader read. And the age of processed update at the monitor is reset to the age of object with the client. And we do this because the reason we adopted this model is we want to somehow characterize the goodness of processed update. And the way we do this is the process update is as good as the goodness of how well the client is working on the input update. And our goal here is to kind of minimize the age of processed update at the client output. So just to give a brief overview of how the age evolves at the monitor. So when an update delivery occurs, for example, at this instance, Z of t is reset to Y of t because it caught an object from client that had age Y of t. And in the absence of any update delivery, the age continues to grow at unit rate. Okay. As usual, we try to understand the system better. So suppose there is an allocation update and the client wants to compute. So the reader hands over this update to the client. The client starts processing. It takes some time to process. And while it's doing that, there is a new update in the memory. Okay? And now after some time, the client finishes the processing, delivers the processed update to the monitor. And now the reader has to read again. It reads again, got this orange update, and the client does the same thing. Okay. This all seems easy, but where's the catch? The catch is, suppose there was an update where the client was too fast with his processing. Now, when the reader has to read again, it will read the same update. And what is happening is that the client is doing some redundant processing, which won't result in any age reduction in the monitor. And this is, in fact, much worse for the monitor. And so this kind of gives us an intuition of what kind of optimal policy we're looking for, is that if the client is too fast with an update, perhaps it should wait for some time. It could be that while it's waiting, there is a new update in the memory, so that when it reads again, it will get the new update. On the other hand, if the client is too slow with the processing, and maybe the optimal thing for the reader to do is to not wait, because there could be another update in the memory and it will get the freshest update. So in the thesis, we do show that this lazy sampling is age optimal. In fact, it should wait for some deterministic function of the computation time t, and it is kind of a threshold policy where the reader waits for beta minus t with a little plus. And you choose this beta numerically that minimizes the age at the client output. Now recall that our goal was to minimize the age at the client output. So if you're waiting to get a new update, does that penalize the age at the monitor? One of the important theorems of this work and of this thesis is that the output always lags input by the computation time. This theorem is funny and interesting because I think this went unrecognized for 10 years. And this theorem can give misleading impression that waiting time or the age of update at the output is insensitive to waiting. What this theorem is in fact saying is that the waiting time affects the age at the client input and output identically. So if the beta minimum waiting policy is optimal for the input, it's also optimal for the output as well. And to conclude this part of research, what we see is that in the producer-consumer systems, it's usually prevalent that the consumers don't have control over how the updates are recorded in the buffer space. And sometimes it also cannot improve the processing. I mean, it's going to take however long it's going to take. But there's still some policies that the consumers can adopt to improve the end-to-end timeliness. And particularly in this case, we see that the waiting policy is effective because it mitigates the high variance of the computation time. So this concludes our part one of the research. In the next part, so up until now, we've assumed that readers had unrestricted access to the memory. Now we'll study the tension between writers and readers, especially when it's prevalent in modern network nodes. We'll also study additional factors affecting the latency and age of the updates. And we'll consider mobile routing application as a unifying application to study these issues. And the way this application works is, suppose there is an application server that sends these app updates. These app updates, of course, arrive through a network to the mobile user. At the forwarder, it maintains some forwarding table that tracks the next point of attachment for the mobile user. And these updates are then kind of addressed properly and forwarded to the mobile. Now, the mobile user moves. When it moves, it sends its new location update to the forwarder to let the forwarder know, hey, I'm at this place, so whatever comes for my address, just send it back to this address. Now, when the application server sends an app update again, it is forwarded accordingly. So first thing to note here is that this fib is usually in real life implemented as a concurrent hash table. So we have a shared memory. And there is a contention between location updates and app updates. So the location updates from the mobile will initiate the write mechanism in the forwarder to update the forwarding table, whereas the app updates will initiate the reader mechanism in the forwarder so that they can be addressed properly. Okay. And but what is the catch? The catch here is if the updates go misaddressed, then they are lost in transit. They're never received by the mobile terminal. And this won't result in any age reset at the mobile, and thereby increasing the age of app update at the mobile. We see that because this is a contention between writers and readers, we have to use some kind of a synchronization primitive. And so if you were using, say, a log-based primitive like RWL, then misaddressed packets can arise if the scenario is as follows. So the reader is reading, meaning there is an app update that needs addressing. So it has to put a read log. Meanwhile, the user moves. So when it moves, it sends a new location update. So now we see that whatever the reader is reading is essentially incorrect because the new location update is waiting at the writer. So in this case, this will be misaddressed. On the other hand, suppose there is a location update at the writer and the writer has put a write log. And meanwhile, there is an app update that wants addressing. It will be delayed because the read request will be denied. It will be asked, will you try again after some time because the writer has now put a write log. On the other hand, if you were using a lockless mechanism, say a read copy update, so this is a problematic state. Why? Because yes, it does allow concurrent progress of both writer and reader, but we see here is that the reader is actually reading an old update because the new update is with the writer, and writer is in the process of writing that update, and it is not published yet. So in this case, again, the app update will be misaddressed. Similarly, if you have a scenario where the writer has already published a fresh update, but this is an old reader, and in this case as well, the app update will be misaddressed. What I'm trying to say here is that freshness of app update at the mobile depends on what kind of synchronization primitive you're using to protect the fib, because it influences if the app update is addressed correctly or not, and also what kind of queuing discipline is employed at the router. So imagine a scenario where you have two updates queued at the router with respect to the AOI performance don't serve the first update, instead do the last come first serve service, right? And you can use this, you can model such scenarios using preemption. And so these are the two factors that highly influence the freshness of app update. And we see that with RCU or RWL, there are many problematic states, and it's not easy to kind of say which of these primitives is better with respect to age. So to analyze that, we developed a stochastic hybrid systems analysis to understand the performance. And before kind of going into the numerical evaluation details of how RCU and RWL works, I just want to focus on the system parameters. So if you think that the location updates are arriving at some rate lambda hat, and the app updates are arriving with some rate lambda, then we're just using the right, this mu hat, the right rate to normalize everything. So whatever I'll present will be in terms of the right time. And so rho hat in this case denotes the normalized user mobility rate, and beta represents the normalized app update arrival rate. So with these system parameters, here I'm plotting average age at mobile user as a function of user mobility. Again, these are normalized results with respect to the right times. And this particular case, I'm setting that RWL reads are 10 times slower than RCU. First thing we see is that as the user moves more frequently, it's bad for age because the app updates go misaddressed. We also see that the penalty of slower reads in RCU. And there are two things happening. First is that because the reads are slower, the app updates are delayed, again, bad for age. And the second thing is, because the reads are slower, it's blocking writer more often, and the writer is not able to write the fresher location update more than compared to RCU. So this is why we see like a RCU outperforms RWL when the reads are too slow for the reader's writer lock mechanism. On the other hand, what was surprising is when the read times are similar, RWL outperforms RCU. And the reason is at higher mobility rates, the fib is likely to be outdated, but an exclusive write lock in RWL prevents the reader to read the stale address. And so whenever the reader reads, the probability of that the reader's reading the good update or a fresher update is higher in RWL than in RCU. So the point that I'm trying to make with this kind of work is, yes, you want timeliness of updates in the memory, and in this case, in the forwarding table, but that comes at the expense of timely reading. And we saw that this tension is kind of prevalent with mobile users sometimes receiving, not receiving an update, and thereby increasing the age of the we have more work on the impact of synchronization primitives on AOI, particularly if we consider RCU. What the way RCU works is the way it allows concurrent forward progress of readers and writers is because it allows the writers to create the copy. So if you want to update the memory frequently, you have to create many copies. But that incurs a significant memory usage. And so we see that there is some age memory trade-off going on in the RCU. And in the thesis, we go into detail about this analysis. Okay, so we talked about the impact of primitives, synchronization primitives on age of update in the memory and with the client. We also talked about optimizing the access for readers to access the memory. What is left? If you look closely at any client, the processing usually involves a sequence of computation steps. So for example, if you consider that collision detection scenario, the first thing the client would have to do it would have to acquire the image from the database, do some sort of feature extraction, and then classify the desired and non-desired objects, right? So even we see that even with this, initial processing, it involves processing that has to have like a sequence of computational steps. And this work, we try to raise questions and answer them hopefully, and how the client can optimize its computational resources to timely process the updates, so that the updates that are received at the monitor represent have the timely representation of the real world. Okay, so the processing a status update at the client is usually dictated by the number of processors available with the client to process the stream of update, and also what kind of policy it is using. So a naive approach would be you have just one server, and it just does a step 1 processing on the blue update, step 2 processing on the blue update, and then when it delivers, it starts processing this orange update. Okay. If you have multiple servers, say you have 2 servers, so you use these 2 servers in a pipeline where each server executes a step in the computation. So you have blue update doing step 1, and then when it finishes step 1, it goes to step 2, and now server 1 starts working on the orange update. Or you can use these 2 servers in parallel, where each server is working on a different update, and it executes all computational steps. Okay, so whether it is servers in series or parallel servers, an immediate question arises: which is more effective in maintaining timeliness? The thing is, it's not straightforward to answer this question because for each setup, we have an explosion of system models. So if you consider this servers in series setup, you can model this system in the following way. Well, if server 2 is busy, an update from server 1 will just preempt the update in service at server 2. Okay, and when the server 1 is idle, it will just start working on a node update. Alternatively, you can have a model where when server 2 is busy, this new update is now waiting in the waiting room of server 2. Server 1 starts working on a new update. And now if server 2 is still busy, it will just preempt the update in the waiting room, such that when the server 2 does finish processing this blue update, it will always have like a last come first serve kind of service. The other way is, well, if server 2 is busy, it can discard the update from server 1. A more conservative approach could be that server 1 does step 1, server 2 does step 2, delivers the update to the monitor, and now does the step 1 processing on it. With the parallel servers as well, there is again an explosion of models. So again, like a baseline scenario would be, let each server work independently on its respective updates. When one of them finishes, it starts working on a new update. Much more, maybe an optimized way would be that you have 2 servers, they're working on the same update. Now, if one of the server goes to stage 2, the other server would be like, well, you're anyways at stage 2, and I should just abandon my processing and start working on a new update. Now, when server 1, in this case, goes to stage 2, and it sees that server 2 is still in stage 2, server 2 would be like, well, you're already in stage 2 with a newer update, and perhaps I should abandon my processing and start with a new update. Okay. Alternatively, there are scenarios where if you're working on the same update and you reach stage 2 first, you just share this intermediate update with the other server. You say, well, I have worked on this update, and now let's come together and work on stage 2. So if the service times are kind of memoryless, this effectively doubles the processing rate at stage 2. So, and now both of them start working on the same update. So the thing is that it's not just the explosion of system models. In fact, what is happening is it's not easy to pick one of the system models and then just start studying its impact on the timely processing. We identified that there is another thing going on with these models, is the concept of wasted power. And we define the wasted power in terms of, you expended computational resources on processing an update that is either never delivered to the monitor or was never age reducing. So for example, in preemption in service model, the server 2 just preempted its update in service. And the question is, well, was it effort wasted because it preempted the update? It kind of expended some amount of time on the blue update, right? And even with preemption and waiting, there is preemption going on. So what it appears like there is a wastage going on with server one as well. And with discarding, we see that server one's effort was wasted. Even with parallel servers, we see that with the baseline setup, if server two, so orange update in this case is a fresher update, it finishes first, so it delivers the update to the monitor. Server one is late, okay, now it's kind of saying, okay, now here is the blue update. But this blue update is of no use to the monitor because the monitor already has a fresher update. So we say that the work that server one did on this update is just useless. And there are other scenarios in parallel servers as well where the effort could be thought of as wasted. So what I'm trying to say is that these observations raise an age power trade-off in these systems, and we want to kind of optimize the allocation of computational resources such that it minimizes wasted power while reducing the age. And the way to think about these systems is if you consider a server farm at an edge or at a cloud, then you have many options to allocate your processors. You can run your processors faster or slower. Of course, if you run your processor faster, it will consume more power. In fact, that power is dependent on the speed you're processing raised to the power alpha, where alpha is some technology dependent factor. And so you have to decide that for a given policy, how much leeway do you get to kind of tune your service rates? And one promising approach to kind of study this age power trade-off is to identify optimal service rates that achieves best age under a power constraint. And based on these points, we can kind of have a optimization problem where where the objective would be to minimize the age at, of course, the monitor. And of course, this age will be a function of service rates at stage one and stage two, subject to the total power consumption being less than the power budget. So in this case, the first term corresponds to the power consumed to process stage one, and the second term corresponds to the power consumed to process stage two. Okay. And this optimization problem also kind of gives rise to another qualitative characterization where we can ask if the processing has just two stages, should stage two be faster than stage one? And if you consider particularly the servers in series setup, then server one is handing out updates to server two at rate mu1, and it generates a new update. And server two is servicing an update with rate mu2. So this rho equals to mu1 over mu2 is just an offered load from server one to server two. And the question we're asking, well, is rho less than equals to 1? And this rho has more meaning conceptually. So if you have a larger rho, this means that server one is feeding server two with fresher updates, but it's also consuming more power. It could be wasting the effort of server one, either by preempting its update or by discarding. On the other hand, if rho is smaller, then perhaps you're not feeding enough updates to server two. Server two is sitting mostly idle, which is again bad for age. So we see that there is kind of an optimal rho and like a sweet spot where you don't waste enough power, as also you're not sitting idle and it's not bad for age. Okay. So if you just kind of reformulate this problem, what we see is that for all the models that we have considered, age will be minimized by choosing the rate of service at stage two to be as large as possible. And in this case, it would be this upper bound that is represented by the right-hand side. Okay. And so this unconstrained problem, so this constraint problem becomes an unconstrained problem where our objective function is just now the age in terms of rho. And what remains is to find the appropriate rho. And here I'm kind of plotting this objective function as a function of rho. It is immediately apparent that for all the models that we have considered, the optimal rho is less than 1. This means that stage 2 should be faster. If it's 1, then stage 2 should kind of operate at the same level as stage 1. And this makes sense because a faster stage 2 doesn't become a bottleneck in the processing, and also allows, for example, if you were using like a queue at server 2 with capacity 1, you will kind of have mostly an empty queue because server 2 is faster, right? And you can also kind of dissect this graph more and divide it into servers in series and parallel servers. The first thing we see is that when you allow preemption in service, so this blue curve is for the case where server 2 just preempts whatever it was working on if it gets a new update from server 1. It outperforms all the other models. What is surprising is if you see this another blue curve, which corresponds to the synchronous service. So you have server 1 processing one stage, then goes to stage 2, and then delivers. It's better than the asynchronous service when there are multiple updates in progress. Okay. With the parallel servers, we see that they're mostly better than servers in series. And the other thing is that for these two curves, the green curve and the red curve at the bottom, this corresponds to a scenario where the servers were able to share information with each other and were able to kind of optimize their workings. Okay, so I want to end this talk by raising an important question, particularly relating to wasted effort. If it's not clear, if you want to understand what the concept of wasted effort is, so you imagine a scenario where a supervisor assigns the same unsolved problem to multiple researchers. Each researcher is working diligently to solve a problem. And in this case, the supervisor is Poincaré, and it says, well, go solve and prove Poincaré's conjecture to Grisha and Martin. And suppose one of the researcher has a lucky insight and has a breakthrough. In this case, of course, we all know it was Perelman, and was able to solve the problem. Now, the person who was also working diligently on the problem, but did not solve the problem first, its effort, the effort he expended might seem wasted. But at the outset, it's impossible to predict which of these researchers will be able to solve the problem first. So while the efforts of other researcher might not contribute to the final solution of the problem, it is not necessarily wasted because it does increase the overall probability of success. So the expected time to kind of arrive at the final solution has been reduced. Okay, and then the question is, well, when does the wasted efforts occur? Well, it occurs when in the case when the server is working on an update older than the monitor has. So for example, in this case, server 2 has already delivered a fresher update to the monitor, and server 1 is still working on an older update. And in this case, whatever work it's doing is just useless. On the other hand, we did observe few scenarios where when the servers were kind of interchanging information with each other, we think that there is no wasted effort going on in those models. And we see that this is in fact seen in the research field and academia in general. And of course, Perelman's work was highly derived from Hamilton's work on Rishi flow, and he just added few analysis and techniques on his work that kind of led him to prove Poincaré's conjecture in 2002. And so just to kind of end this talk with a final recap, we focused on the producer-consumer systems with the system model where we wanted to kind of analyze the age of updates in the memory with the client and with the monitor. We divided our work into 3 broad classes. I'm just kind of highlighting the major things that we discovered while studying such problems, is that if you were to kind of optimize the memory access, and if you have no control over or how updates are recorded in the memory, then perhaps waiting is okay if there is a high variance in your computation time. For the second part, we also kind of explored this contention prevalent in modern network nodes. There are millions of packets going in and out of the network. And what was surprising to see is that lockless though, because it doesn't delay writers and it doesn't delay readers. It seems like it should be favorable to age, but it's in fact not, because we saw that there are scenarios where there were significant misaddressed packets and it was not good for age. So lockless is not always better than lock-based. And for the final part, we studied this age power trade-off in parallel and pipeline servers for, again, a special case of two-stage processing. And we discussed this notion of wasted powers in any kind of model that you consider. So with this, I'll just end my talk. I'm open to questions now, but before that, I just want to thank everybody, my committee members, people who are here, my peers, my colleagues, my family, for everything. So thank you.
Okay, I think we have time for questions. I think we're doing pretty good on time. Is there a way to see everybody's faces up there? Like we have a box for audit. There we go. That's better. You guys don't have to turn your cameras on. You're
So maybe I will say that this was such a nice presentation. It was very clear, very nice presentation, and also the work is very nice. I mean, so you thought about various very interesting aspects in this read-write domain of age of information. Yeah, I don't have any immediate questions right now. Maybe if as other people ask questions, maybe I will ask questions. But this was perfect. Very nice.
So, hi Vishakha. So I thought your talk was really good and you were able to abstract out the most important points in a very lengthy study that you did. So it was very good and you kept me up to date on the analysis. So I don't have any questions for this group here. Could you just comment on future work in terms of somebody wants to carry this forward? Is there something specific, a scenario like a router model that could be looked at where you think there's some still more research to be done? I mean, some of the things, shared memory architecture, is covered by what you have been doing here.
Sure. I mean, of course, any thesis kind of comes with a considerable work that needs to be done. So if I go back to my slides here,
I think there may be a problem with the connection. We lost Vishakha's. Oh, okay, she's back.
sorry about that. I don't know what happened.
Sorry.
Can you hear me now?
Yes, we can.
Let me.
Click at the tabulary folder up there.
Okay, let me see
Right
if
at
I
the
can.
top of the screen. Recording in progress.
So
Oh, sorry, that's me.
So, so with respect to your question on, how this work can be kind of extended to routers. Well, in this case, the baseline study just involves one reader. You can have multiple services. For example, in software-defined networks, you can have multiple services that are running. And so you would have many, many readers coming in and trying to access, say, this forwarding table because they are kind of servicing different types of users. So in this case, you can extend the study with, considering many readers as well as many writers, because there could be some kind of migration going on that needs, and where you kind of need to track the IP address of the next edge cloud that you'll go to. So, and not just one application of serving an app update to the mobile terminal.
Okay, good, thanks.
Yeah. So I didn't get in the server node in the part 3. Is there some cost associated with these servers running, or you're only looking at the cost of asking for updates?
You mean this particular setup?
Yes, for example.
So your question is that you
You were talking about wasted effort.
Right.
How is effort? Do you have to pay the server to, like, say you had those two researchers working on a
Right, yeah,
project.
yeah.
So where is the cost coming from? Is it just the effort, or you are actually paying for some computing time?
We're thinking of paying in terms of power consumed
By the servers.
by the servers, yeah. Because if you are in a server farm, the way I think I'm imagining the scenario is you would have many services running, and you have to optimize the power allocation between each of these services. And then you are doing this kind of timely processing of updates for some real-time application, and you have some some processes that are available to you, but you have to kind of optimize them with respect to the power allocated to you. So that's the scenario that we're considering. That you'll always waste effort no matter what you do if you want to reduce the age.
Yeah, that I'm not sure. So for example, in some similar models that we were looking at, yeah, you're looking at the geometric arrivals. Yeah. So suppose I ask two things to happen in parallel,
Okay.
and I'm waiting for the first one to finish, right?
Yeah.
First person who will solve this conjecture. For some distributions, both cost and performance go down up to a certain point. For exponential, they say the same, and for some lightweight, cost goes up a little bit, but the performance goes also up. So, and the reason is, for example, if it were not for the other guy, the Grisha, what was the person who was working in parallel, he would have stayed much longer.
Yes, yeah.
So in that sense, both cost and performance, there can be improvement in both, meaning cost can also go down.
Oh, okay, yeah. Right.
That's another. Anyway, let me let other people ask, and then I can wait a little.
Yes. But I think you raised an important point and a nice point. I never thought about that. Like the effort of Dunwoody would also be kind of
longer,
extended if it weren't for Grisha, if he did solve it.
Exactly, but it depends if because these are random times of finishing. It depends whether this distribution is heavy tail, light tail, or exponential.
For our case, of course, we are adopting memoryless service because, yes, it's easier to track. And one of the, I mean, if I had like an X amount of time and money to spend on this problem, I would rather just sit down and build a simulation of even with this two-stage processing. And as you described, if the distribution is different for processing, how does it affect the wasted power and the age?
Yeah, I can show you later some kind of things. But another thing, I really like how you made like one line summaries. But maybe having even a little bit of a table that goes into a little more, it's still a summary, but just provides a little more detail. We
Okay.
also-
Sure, thank you.
What are these?
So like just I'll follow up on this one. So say that you have tasks to be executed at the server.
Yeah.
Do you think like say that I have multiple servers that I can deploy different vertical split of the tasks on? Do you think it might be worth it?
And
to-
multiple servers.
It's just like, you know, your division of step 1, 2, 3.
Yeah.
But do you think it might be worth it to just take a look at the computing capability of each server?
Yeah.
And decide, you know, what are the steps that may be better to place on the same server? And what are some that may be better to, like maybe a
Yeah.
few steps,
Sure, yeah.
more computation intensive, place on more powerful server, and then the others place on.
Right, I mean, that's like an important point. What I think what you're talking about is much more granular optimization of the computing steps. Well, of course, you can do that, but again, I think in that case, the overall constraint remains same, even if you have like a more powerful processor. Of course, the more powerful processor will consume more power, right? And
But I guess that's my kind of follow-up question, like, do you think it might be worth it to, like, I think one of your conclusion was that you could kind of, adjust the
Speeds of the process.
service rate.
yeah,
Service
right,
rate,
it's,
adjusted the circuit rate, to reduce the power.
yes, okay,
Like, can that be used in some sort of, you know, kind of energy efficient service, context?
sure, but if you reduce the service rate to
Will increase
reduce
the-
the power, but it will penalize the age.
Uh-huh.
You're kind of, you're servicing slow, any job, and it would be delivered late. So again, I mean, there is trade-off. How you,
I
But-
just comment, there's lots of work to do in this area of thinking about adjusting the speeds of the processors, the service rates. Maybe because in an age-dependent way, like if the age is bad, maybe you want to work a little faster to make it better. There's many related problem formulations, even just with one processor, right, that are unsolved. You know, in this work, all these models with 2 processors and 2 stages. Like we only looked at exponential service times because we already had this combinatorial explosion. And that gets multiplied again. You start looking at you know, other kinds of related models.
I mean, one of the model I think you can study with your Chinese collaborators, where if you know, if you're spending like you've already spent a significant amount of time on processing, should you now increase the speed of processing to deliver the update, or what do? You start again with a new update? So again, like as Professor mentioned, even with a single server, a single CPU, you can kind of optimize the job in batches and decide what power you want to work on each batch.
So you should come up, maybe come a little closer to the microphone. Go online and there.
Yeah, just grab the seat. So, since you're both the servers, they need to know about their constant stages of processes, like where they're, what stage of processing they are at.
Not necessarily.
No.
So in this, so I described one of the models where if I have to go through. So in this case, both of them are working independently of each other's knowledge. So server one is working on blue update without sharing the stage information or the intermediate update information with each other. On the other hand, the next model that I described was, you have two servers that are working together on stage one. And if one of the server finishes stage one first, then the server one, then it would be like, well, I'm already on stage two. And then it's of no use if you work on stage one.
So how is that communication being made between server two and server one?
There could be a message queue between two servers.
Okay, so there are kind of any overhead about the communication? between the two?
For this model, we're not assuming any overhead, but yes, there can be an overhead in terms of how frequent you're sending this message to the other server and how long is the queue.
There are lots of overheads that we've neglected all of them. Yeah.
So can I follow up with a question?
Yeah.
Yeah. So I have a couple of questions here. Maybe I will start with you talked about server farms. Let's say you have a lot of small servers that you can turn them on and turn them off depending on the load that you have currently and the ages of the packets in the system. In a way to control, as Roy was saying a moment ago, control the total server rate as a function of the load and the current ages. Have you looked at that kind of problem?
No, not for these setups where you require like a sequence of computational steps. No, we have not considered, but I think if this is kind of answering your question, there is a group that works on just considering a problem where you have a single CPU and then you try to optimize the batches and like how fast the batch should work within a particular job, if that makes sense. But not with respect to if you have multiple CPUs and then how can you kind of how can you operate one CPU at a faster rate if you're kind of already late with a job. So
Which paper is that?
I think they're talking.
Oh, you're talking about the work I was doing?
Yeah.
Oh, we had an Infocom paper about CPU speed up and slow down this summer. But I think Shenner, in some way your question makes me ask, are you thinking about situations where there are multiple sources or just a single source? Because when there's multiple sources, then and multiple age processes that you're trying to sort of control, there are lots of questions still about how to allocate servers to these different streams. When there's a single source, like in these scenarios that Vishakha has looked at, in general, like, there's pretty limited return in doing parallelism on these systems, right? Like you can have two or more servers working, but are they, if they're working on the same update, maybe one will finish a little faster. In an exponential model, they will, but as Amina points out, answers can be different for other service time distributions. And, in some sense, we for a single source, we've considered all of these variations on what you can do, the results are still somewhat ambiguous, but in general, adding a lot more servers doesn't help so much. Is kind of a qualitative.
Yeah. Yeah, interesting question, interesting problem. So the other question I had for Vishakha, that's also related to this conversation is, as you said, like there are lots of regimes of operating queues, like you can do preemption, no preemption, dropping, waiting, preemption in waiting, and all of these things. And as you said, you know, there's an explosion of different kinds of models, and typically for a paper or, you know, for a problem, we focus on one model and do our best, you know, analyze it and maybe sometimes optimize it in best we can. But, you know, my observation has been that in some regimes, something works better. In some other regimes, some other thing works better. I wonder if there could be an analysis, kind of like a meta-analysis, which optimizes overall, you know, chooses in whatever regime that you are at, choose the, you know, operating system model that works the best in that system, and somehow do an overall analysis kind of thing. In other words, like preempt when preempting is the right thing to do. Don't preempt when not preempting is the right thing to do. Have you tried anything like that, or what are your thoughts on this problem?
So my thoughts are, so if you consider one of the setups here, for example, if you consider preemption in service, the existing, I think, view with preemption in services, it's always age reduced. I mean, it's better than most models. You know, if you just consider even one server, right? And the thing is that that analysis involves exponential service. Now, preemption is usually heavy if you consider actual systems where if you preempt a job, to start a new job, you will have a setup time. Okay, so within this system, you can kind of optimize. Well, if the setup time also has some kind of memory-less distribution with some mean time different from the actual service time, and then you have an additional service of, you know, exponential service of actually servicing the job, well, then how does preemption in service perform? You just, even with that this particular model, and then this kind of again explodes to multiple models where if you're preempting an update in the queue, is it always exponential? Like, can you kind of model it in that way? What would be the appropriate rate to choose? And so I don't know if this answers your question.
Yeah. Thank you. Yeah.
I guess we're sitting here looking around the room to see if anybody else has anything to ask. Looks like they're all smiling, and I think they're done. I guess this finishes the open portion of the defense, and I guess we should thank Vishakha again, and then. Okay, all right, thank you, everyone.